Hello there, welcome to this new lecture about binary heaps. So first of all, we are going to introduce binary heaps, which is a data structure based on trees, more precisely on complete binary trees. That is, the binary part of the tree means that each node has at most two elements, two childs, and the complete part means that for every level it contains the maximum number of nodes, that is, two nodes per parent, except for the leaves, which can contain less elements. And another property is that the tree contains a partial order. We will talk about that later. And finally, a very interesting property is that it can be easily represented as a vector. So, regarding the first part, the complete binary tree means that per level we have the maximum number of possible nodes, two per parent, and the other possibility would be that the bottom level that contains the leaf is not fully completed, but always it contains the nodes from left to right. Regarding the partial order, we are going to consider two characteristics. The first one is the minimum value of the tree is always placed at the root, and also that each subtree maintains the heap properties. In this case, we are considering the minimum value at the root because we are going to work with what is called min heaps. There's also its counterpart, max heap, which has the complementary property of having the maximum value at the bottom of the tree. Finally, as I was mentioned, it can easily be represented at a list just by going through the tree level by level from left to right. So in this case, the root will be the first position of the list. Then at the next level, we have positions 1 and 2, then 3, 4, 5, 6, and finally position 7, 8, and 9. Of course, this could be adapted as many elements as the tree contains. So, if we recall the basic operations we defined at the previous lecture, we have the length of the queue of the binary heap, which in this case, since it's represented as a list, we can reduce the problem as just computing the length of a list. Obtaining the minimum element is also trivial, since it's always placed at the head of the list. It's just accessing to the first position of the list. And the two interesting properties are removing that minimum element, the first value of the list, and adding new element to the queue. So if we see removing the minimum element, as we have already mentioned, minimum element is the root, so we will need to remove the element. But if we do that, then this tree is no longer a heap. So what we need to do, besides removing the element, is restoring its properties. The complete property is easy to restore. We can do it just by taking the last child, in this case the leaf from the bottom level, the rightmost one, and just place it as the new root. This maintains one property, but not the heap property of the order. To maintain this property, we will need a second operation called heapify, that we will talk about that in a moment, but it's basically starting from a position just to maintain the order. Talking about the cost of the operations, we can have the intuition that this operation will have two parts. The first part is computing the minimum, which, since it's just accessing the first position, it has a constant cost. And the most important part is the cost of heapifying, which will be the real cost of removing the minimum. And we will talk about this in a moment. So, as already mentioned, we need to heapify to guarantee the heap properties of the order. We are going to do this just using recursion. Once we have placed the child as a new root, we are going to heapify from the root position. And what we're going to do is create a recursion function whose basic case will be to check if the element is a leaf. Leaves are already heaps, so the moment we reach a leaf, we are done. If it's not a leaf, then we will need to find whose child, left or right, has the smallest value. When we find it, we will compare that value against its parents, the position we are heapifying, to see if it's small or not. If it is, then we will swap places and make a recursive call to heapify from the child's position. If it's not, then we're done. So if we see this with the previous example, remember we have removed the 16 and placed it as the new root, and we are heapifying from that position. And what are we going to do? Since it's the root, it's not a leaf, so we need to find the smaller child. In this case, from 7, 5, the smaller will be 5, and we compare 5 is smaller than 16, yes. Then we need to swap places and make a new call. 16 is not a leaf, so we will need to find which is the smaller child. In this case, 7, which is also smaller than 16, so we will need to swap places. New recursion, 16 is already a leaf, we are finished. And regarding the cost of this operation, we will have a logarithmic cost that will depend on the depth of the positions to heapify. The other operation is adding an element, and we have to take into account when adding elements, of course, we will be at the bottom of the list, the last position of the list, which is the last position of the bottom level of the tree. Why? Because we need to maintain the complete property of the tree, of the binary tree, and we also need to maintain the order part. So what we're going to do when adding a new element is look for the bottom level in the rightmost position, or the consecutive position to the rightmost leaf, and in this case it's here, we will insert the element here. In this case, we are going to consider inserting the element of value 4. At this point, we have successfully maintained the complete structure, but we need to maintain the order. To do that, what we are going to do is check for the parent of the position we have added. We need to see if the new value is smaller than its parent. If it is, then we will swap it. And this process will be repeated until that property is no longer true or we reach the root of the tree. In this case, we are at this position with value 4. We look at its parent, which is 7. Since the child is smaller than the parent, we will need to replace them. One more time, we look the child and its parents. The child is still smaller than the parent, so we will swap them again. And in this case, since we are already at the root of the tree, then we have finished. Regarding the cost, this operation also has a logarithmic cost. Finally, we are going to see how to build a heap, not from scratch, but almost. In this case, we are going to start with a list that does not contain any particular order, and we will build the heap out of it. So this has 3 different steps. The first is create the heap, just following the list of the order of the list. That is, the first position is the root, and so on and so forth. And when we have the structure, we need to maintain the heap property. For that, we will look for the parent of the deepest leaves, since leaves are already heaps, and we will be heapifying from that position. So if we see an example, we are going to start from that list. The first position will be the root, and so on. So we build the heap. In these cases, leaves are already heaps. We don't need to do anything, and we need to look for the first element that is not already a heap. In this case, will be 16 value. What do we do now? We need to heapify that subtree. If we see 16 is bigger than 7, so the heapify that we have already shown, what we have as a result is swapping the places. So now this whole subtree is already a heap, so we move to the next node. So we're going to go from right to left, going backwards. In this case, the next one will be this one, has value 2. We will heapify from that position, and in this case, if we look at it, that subtree is already heap, so heapifying that will have no effect. Then we proceed to backwards to the previous one. In this case, that node, that subtree is already a heap, so again we don't need to do anything. So now we go to the previous one, to this position, and if we heapify the value, again we'll have no result because it's already a heap. So we move backwards, we heapify from that position, which, since it's not a heap, we will repeat the heapify procedure, and we will obtain this value. And what is the cost of this operation? Because in this case, it will be n log n, since heapifying, remember, that has a logarithmic cost, and we are going to be heapifying more than one time. And that's everything for this lecture. Thank you.